Hello friends, welcome to today's chemistry lesson where we are going to talk about pure substances, mixtures, and how to separate mixtures once they're made. We've got a lot of new vocab and some new concepts to cover today, so we're going to jump right in with the differences between what a pure substance is versus what a mixture is. All right? A pure substance is one thing, right? So whether that is an element or a compound, when we have a pure substance, when we say something is pure, it is only the substance you say it is. For example, if I have this really cool ring, and this ring is told to be pure gold, then the only substance I should find in this ring is gold. Right? It should be 100% gold atoms. Right? There shouldn't be any iron, there shouldn't be any silver, there shouldn't be any platinum, there shouldn't be anything else. Right? So fantastic definition there. A pure substance is an element or a compound that is untampered, right? It is totally pure. There is nothing in it other than that substance, right? The same thing goes if I have a glass of water. Look at how photorealistic my drawing skills have become, and I say this is a glass of pure water, right? And I say this is a pure substance, this is water. That means the only thing that is in this glass is H2O. There is no salt, there is no mineral, there is no iron, there is no calcium, there is no nothing. It is just pure water. Right. For a substance to be pure, it must contain only atoms or molecules of the thing that is said. Right? If I'm saying pure gold, it should have only gold. If I say this necklace is pure silver, there should be only silver atoms in it. Right? So that's a pure substance. An element or a compound that has nothing else mixed with it. Which brings us pretty nicely into the idea of a mixture. Right? A mixture is a blend of two or more kinds of matter. So the alternative to these things, right? If I say this ring is gold, but it is in fact just plated with gold, right? If it's a plated ring, right, that means there's gold on the outside and, let's say iron inside. Right? If you've ever gotten a ring from somewhere cheap that turned your finger green after wearing it for too long, that was something that was plated in copper. Right? It's not a pure substance. It's multiple. Right? A mixture is a mix of multiple pure substances. Let me think about that. That, at first glance, looks like a good definition. Can I think of anything that might make that not a good definition? I'm going to go with, that seems fine. A mixture is a mix of multiple pure substances. Right? They don't have to be pure substances. It just could be a mixture of multiple substances. But yeah, saying that taking multiple pure substances and putting them together, that does make a mixture. Right? If I say we have salt water, right? I go to the ocean and I pull out a glass of delicious, wonderful ocean water, right? This is salt water. Right? A mixture can also be made of multiple mixtures. That's true, but still the definition of mixture would just be multiple kinds of matter. Right? So the start, where it's just multiple pure substances, is totally fine. You can mix mixtures, but that would just be even more pure substances if you keep breaking it down. right? We'll run through an example in a second, right? So if I have salt water, right out of the ocean, delicious, wonderful, hydrating salt water, this is two different things, right? This is the pure substance NaCl, right, for salt, and the pure substance H2O, right? Each piece of my mixture retains its properties, right? I have salt and water, right? If I take a sip of this, it is salty and it is water. I don't end up with something totally different, right? I don't mix salt and water together and end up with lettuce, right? I don't just like make something brand new. It's salt and water. I haven't chemically combined these things. I just mixed them together. And when you mix them together, each piece keeps its properties. Right? Or diamonds. Yeah, I don't mix salt and water and end up with diamond. Right? I don't end up with something new and different. I end up with salty water. Right? Let's say I also have a second mixture, and that mixture is chocolate chip ice cream. Right here is a perfect cone of chocolate chip ice cream. Each of these things, right, we have two different substances, right? We have vanilla ice cream and we have chocolate chips. Right? Two different substances. And we can break these down further, right? So like we were saying, or like Darren was saying before, right? A mixture can be made of multiple mixtures. That's true. I could keep breaking this down until I find the pure substances that make it. But at the end of the day, it's just a bunch of pure substances. But if I have chocolate chip ice cream, this is a mixture of vanilla ice cream and chocolate chips. When we want to talk about mixtures, we can differentiate them into two categories. We can say that they are heterogeneous mixtures, which means that they are not uniformly mixed. Or we can say that they are homogeneous mixtures, which are uniformly mixed. And our salt water and chocolate chip ice cream are good examples, one of each. Our chocolate chip ice cream is a non-uniform mixture. Every bite of chocolate chip ice cream does not have the same amount of chocolate chips and ice cream, right? That ratio is not going to be the same. I can have one bite in the beginning that's just vanilla ice cream, and then at the end I could have a little bit of vanilla ice cream and a bunch of chocolate chips as it melts, right? It's not uniform. Every sample is not the same. Whereas with something like salt water, every sip you take of salt water is equally salty, right? There's not more salt at the top or more salt at the bottom or more salt in the middle. The salt is evenly spread and evenly mixed throughout, which makes it a uniform mixture, evenly distributed. Right? If you have Minute Maid lemonade or Kool-Aid or Nesquik powder and you use that to make the resulting drink that comes from that. If you put protein powder in a smoothie or something like that, right, you end up with a uniform mixture. You've mixed your two things together, or you should have mixed your two things together to the point where every sip, every bite, every sample you take is the same amount of thing A and thing B, right? If you've made lemonade, you can't pull the powder out of the lemonade and be like, well, there's more powder at the top or more powder at the bottom. It should be evenly mixed throughout. All right, so quick recap. Pure substance is an element or compound by itself, untampered, to use Filippo's word, right? Totally by itself. A mixture is a blend of two or more different pure substances, or two or more different mixtures, right? Tomato, right? It's multiple kinds of matter put together in the same spot where each piece retains its properties. right? Salt water, my salt is still salty, my water is still watery. My chocolate chip ice cream, my vanilla ice cream is still vanilla-y, and my chocolate chips are still chocolated chippy. I don't know where I was trying to go with that word, but that's fine. And then within our mixtures, we have evenly mixed things, right? Homogeneous mixtures where things are evenly mixed together, like our salt water. Every sample is the same. And we have non-uniform or heterogeneous mixtures where every sample is not the same, right? Like every bite of chocolate chip ice cream. From there, we've got some practice. Right. The air around us, right? You take a deep breath in, and then 5 minutes later, you take another deep breath in. Right. Is that air that you're breathing in a pure substance, a homogeneous mixture, or a heterogeneous mixture? 10 seconds on the clock. If you need more time, pause the video. So, the air around us is a homogeneous mixture. Right? The air around us is made up of multiple different gases, right? So we can cross out pure substance right off the bat. It's not pure, right? When you breathe in, you're breathing in oxygen, carbon dioxide, nitrogen, argon, a bunch of different gases that are in the air. Right? You breathe out carbon dioxide, you breathe in oxygen and everything else, right? You add the other gases back into the air, it mixes together, you breathe it back in. So we're looking at the difference between homogeneous and heterogeneous. Is it uniform or is it non-uniform? Right. Is there a place in your room that has more oxygen than any other place? If I take a breath over here by my computer, deep breath in, and then I get up and I walk over there to the closet and I take another deep breath in, do I get more oxygen somewhere in my room? No. Right? Everything is mixed together. Each breath of air that I take in is the same. Right? There's not a spot where all the oxygen pools together. Right? It's not like I can't breathe over here by the computer because there's no oxygen over here, but if I walk to the closet, I can breathe really well because that's where all the oxygen is, right? It doesn't separate itself out and clump into different spots. It's all evenly mixed together, making it a homogeneous mixture, uniformly mixed together. Every sample you take is the same. Every breath you take in is the same. All right, what about this one? An example of a heterogeneous mixture. What thing would be non-uniform? Right, which of the following choices would be a non-uniform mixture? And here, for our answer, we're going to get soil as the answer. Right? The other three things here are all actually pure substances. Right? Sugar, when I say here is a bowl of sugar, there should only be C6H12O6 in that bowl of sugar. If I say this is carbon monoxide, there should only be carbon monoxide there, right? Calling compounds by their names tells me that it is a pure substance, right? Saying this is water in the scientific sense should mean that this thing that I'm holding is only H2O. Saying this is iron should mean that there's only iron in this thing that I'm holding, right? Whatever it happens to be. But soil, if I take a scoop of soil from the south side of Central Park and then a scoop of soil from the north side of Central Park, those scoops of soil are not going to be the same, right? If I take a scoop of soil 10 feet apart in Central Park. They're not going to be the same, right? There's all sorts of different things that go into soil that make it different, right? So you might find a rock in your first scoop and no rock in your second scoop. There might be a worm in your first scoop and no worm in your second scoop, right? It is a mixture, and you can tell what's in it, and you can look at all the different things that make it up, but it is not uniform. It is not evenly mixed together. So keeping going, when you have a mixture and you've put two things together, something else you get to do is unmix them, right? You get to take them apart. And there's a couple of different ways that we get to take mixtures apart, but the important thing is that you can take mixtures apart without using a chemical reaction, without actually having to do chemistry in its basest sense. If I have my salt water, right, from before, I went and I mixed some salt and water, I can separate my salt and my water by heating up my mixture and boiling away all the water. The water is going to boil away, and at the end, the salt is going to be left as a pile on the bottom of my container. And I've separated my salt and my water. Right? That's another physical mean, right? Boiling away my water leaves me my salt, and I've separated my mixture. I still have salt and water, but I no longer have salt water all at once. Right? If I have my chocolate chip ice cream, and I don't like chocolate chips, right? I just want vanilla ice cream. I can go in there with a spoon and pull out all the chocolate chips. Right? That's a thing I can do. I don't know why you didn't just order vanilla ice cream if you didn't want chocolate chip ice cream. That's on you. But if you got chocolate chip and you only wanted vanilla, you can go through and pull out the pieces that you don't want, right? You can separate that mixture, and you can get the vanilla and the chocolate chips. Certain things need a little bit more specific methods, right? If you make coffee in the morning with a more old-fashioned coffee maker, you have a coffee filter that catches all the grounds of coffee so that the only thing that pours out and goes into your mug in the morning is the coffee that you want to drink, right? And a piece of filter paper, right? This almost trapezoid that I'm making here, right? This piece of filter paper is a piece of paper, a piece of cloth that has really small holes in it that catch big particles like coffee grounds and lets the coffee drink all the way through. Right? It can't catch the drink in the filter paper, so it goes through, but the coffee grounds, the bitter leftover parts of the beans, stay up top. If you have sand in your water, right? You've got this thing and there's sand and water mixed together, and you pour that through a piece of filter paper, you will end up catching all the sand on top because it doesn't fit through the holes, and the water will pour through, separating your mixture, right? You can filter things out like that. It doesn't have to be one liquid and one solid, right? If I talk about a coin machine, right? If you remember the things at the bank that take all your coins and sort them and tell you what how much money you have, right? Those work by filtering out your different coins, right? They filter them by size. So they have a thing inside here with a hole big enough to catch or a hole where only the quarters get stuck, and there's a hole big enough for everything else to fall through. Another one where they catch only, what's the next biggest coin? A nickel, and everything else falls through, and then they catch the pennies and everything else falls through, and then they catch the dimes, right? So they filter them by size, and that hole gets smaller and smaller so that the bigger coins get caught first and the smaller coins get caught last. And that's another way of filtering, just separating things based on their size and letting some things through and catching others. Distillation is another thing that we talk about when we're talking about separating mixtures, and distillation is specifically separating two or more liquids based on their boiling points. Right, and distillation is a neat technique that I'm gonna try my best to draw a distillation apparatus. Nope. Right, so a distillation apparatus looks something like this. And if I start with a mixture of two liquids, let's say I start with water and alcohol, and I want to separate these two liquids, right? I can't filter them because they're two liquids that are mixed together. But what I can do is separate them using their boiling points. Right? Alcohol has a boiling point of around 85 degrees Celsius. Water has a boiling point of it's exactly 100 degrees Celsius. So if I heat this mixture up, right, I turn on my fire and I heat this and I get this to 90 degrees Celsius, that's going to make the alcohol boil, but it's not going to make the water boil. So slowly the alcohol is going to be pushed up and then get stuck to the side and drip its way down into here, right, while the water stays exactly where it is. And so eventually you're not going to have any more alcohol in the bottom container. All of your alcohol is going to travel up, get boiled out, get trapped on the side of the container, and drip its way into here. So now you have your water and your alcohol separated. Right? You can do this for 3 liquids, 4 liquids. You can do multiple distillation kind of tiers, which is kind of annoying. And by kind of annoying, I mean very, very annoying. But frequently is used just to separate 2 liquids from each other. Right? If you boil one but leave the other cold enough to stay a liquid, you can get one to leave and the other to stay. Right, and there's all sorts of other physical means for separating out mixtures. You can use the properties that some have that others don't, right? Go to the needle in the haystack, right? Here's my fantastic haystack, and there's a needle in there. If I use a big, giant cartoon magnet, I can pull the needle out, but leave all the hay where it is, right? Using the magnetism property of the needle, right? The magnetic property of the needle that the hay doesn't have to pull one out and not the other. You can separate things based on their density, right? This is one of the labs that we could do if we were in person, but if you can separate things by density, if you have a bunch of almost identical things in water, you can add salt to the water, and that'll change the density of the water, making the lighter or less dense things float, and you can scoop them off the top. You can just do that over and over again until you have everything separated out by density. Basically, any property that one piece of your mixture has that the other pieces does not have is a way that you can separate the mixtures. If one thing is magnetic, you could use magnetism to separate that one thing out. If one thing is very dense and the other things are not very dense, you could use density to filter that one thing out. If you have multiple metals mixed together, so that's another common one, is like brass is a mixture of zinc and copper, but they are melted and stuck together. You can just melt the two of them again and separate them out based on their density or based on their distinct properties. All right, there's all sorts of ways to unmix mixtures. And with that, that's actually our whole lesson for today. And with that, we're going to jump over to our Google Meet. And we'll take attendance. I've got a couple of announcements, and I'll see you all there.